Hi students, now we will discuss about the potential energy stored in an electric dipole when it is placed in an uniform electric field. That means if a dipole is placed in an uniform electric field, then we know a torque will act on it. So when this torque will act on it, then how much potential energy is stored in this electric dipole? Now we will discuss about that. So here at first see these two diagrams. So here for the first diagram, the dipole is placed by an angle θ1 with the electric field E. For the first case, the dipole is placed by an angle θ1 with the electric field, and a torque will act on it. So if a torque will act on it, we know that if torque act on any object, then the object starts to rotate such a way. So here this dipole also starts to rotate, and for the after a few time the position of the dipole is such a way, here the angle between the dipole and electric field is θ2. So here the angle was θ1 between the dipole and electric field, and as it starts to rotate due to the torque, after a few time the angle becomes θ2. So during this rotation of this electric dipole, some energy is stored in that dipole. Now here suppose I draw one diagram. Here at first this is the position of the dipole, then after a few time it is slightly rotated and the angular displacement is d theta. So if the angular displacement is d theta, for this angular displacement, what is the work done? For the linear motion, we know that the work done is equal to force into displacement. But for this rotational motion, we will calculate the work done such a way that work done is equal to applied torque into angular displacement. So here for the small angular displacement d theta, let the work done is equal to dw. For the small angular displacement d theta, let the work done is equal to dw. So we can write that dw is equal to torque into the angular displacement, that is d theta. So dw is equal to tau d theta. So such a way, by the small angular displacement d theta, again d theta, again d theta, such a small angular displacement, the electric dipole will take the position θ2 if it starts its motion from θ1. So at first this one, the electric dipole was placed by the angle θ1, then slightly rotate d theta, slightly rotate d theta, slightly rotate d theta, and at last suppose the position is by the angle θ2. So from θ1 to θ2, as the dipole rotate, how much work is done? So we have to integrate the small work done for the small angular displacement, because from θ1 to θ2, from θ1 to θ2, here several d theta is there. At first θ1 to d theta is changed, again d theta is changed, again d theta is changed, and at last it will reach to θ2. So for each and every d theta, dw work is done, dw work is done, dw work is done. So if we calculate want to calculate the total work done when the dipole starts its rotation from theta 1 to theta 2, then we have to integrate this dw. That's why for the total work done, we integrate this, that is dw, integration of dw is equal to tau d theta from where theta 1 to theta 2. Now here the total work done w, and here theta 1 to theta 2, tau means we know that p e sin theta, and this is d theta. P is the dipole moment, is the electric field. Now from here w, p will be, the p is the constant, so out from the integration part, so theta 1 theta 2 sin theta d theta. So from here w is equal to p e, what is the integration of sin theta? That is minus cos theta. So here minus cos theta, the limit is theta 1 to theta 2. So after that right line again, that is p e minus cos theta 1 to theta 2. This minus we put outside, so minus p e cos theta, this theta 1 to theta 2. So here at first we put the upper limit, so at the place of theta we put theta 2, that is cos theta 2 minus, here we put down lower limit, so cos theta 1. Now w is equal to, we just put this minus sign inside, so that is p e, then that will be plus, that is cos theta 1 plus minus cos theta 2. So this is the work done when the dipole starts to rotate and its position from theta 1 to theta 2. And this work done will be stored as a what? Potential energy. This work done will be stored as a potential energy. Therefore we can write the potential energy, P means potential energy, is equal to what? P e cos theta 1 minus cos theta 2. This is the expression of potential energy stored in an electric dipole when it is placed in an uniform electric field, and obviously the dipole when rotating in the electric field. Okay, so potential energy is equal to P e cos theta 1 minus cos theta 2.